Okay.
Hello, everyone. Let's start the final presentation of this session. The title is Quadratic Transform for Fractional Programs in Signal Processing and Machine Learning. The speaker is Professor Shen from the Chinese University of Hong Kong. Let's welcome.
Okay, thank you. Thank you for the introduction. And thanks for coming to my talk. So for those who are familiar with mathematical optimization, I can summarize what I'm going to say in one sentence. I will decouple multiple ratios for the fraction program simultaneously so as to make the problem easier to solve. For those who are not, I'm going to elaborate on that. Okay, does not work. No. All right, okay. So my talk comprises 4 parts. So let me start with the background of the fractional programming. So, fractional programming, namely FP, has a long history. It refers to a class of mathematical optimization problems that deal with the ratio terms. Well, the FP was first studied by von Neumann in 1937 in order to study a problem from economics. But my talk focuses on the latest progress in the field of FP. So I will talk about new methods as well as new application cases of FP. Okay, so let me start with the simplest case of FP problem, the single ratio problem. Suppose we have a pair of functions a and b. In particular, we assume that a is non-negative and it's concave in variable x, and the denominator function b is strictly positive and it's convex. So what I want to show here is to maximize the ratio between a and b. And since we have only one ratio here, this problem is referred to as the single ratio problem. Even though a is concave and b is convex, this single ratio problem is still not convex in general. So solving it directly will be very difficult in general. So the difficulty of the single ratio problem is caused by the coupling between a and b. So a natural idea is to decouple a and b in order to facilitate the problem solving. And this idea can be implemented by the classical Sharnis-Cooper algorithm. So its main idea is to rewrite the problem in this form. As you can see, a is kept in the objective function while b is moved to the constraint. You can see that 2 auxiliary variables q and z are introduced. And it turns out that the new problem is jointly convex in x, q, and z so long as a is concave and b is convex. And therefore, the originally non-convex problem can be converted to the convex problem so that the standard optimization tool can be applied to get the global optimality. But this is not the only way to decouple the ratio. Another classical method called Dinkelbach's algorithm decouples the ratio in a totally different way. So recall that we wish to maximize a over b. So in principle, we wish to make a as big as possible and make b as small as possible. And therefore, a can be basically thought of as the utility and b can be thought of as the penalty. So a natural idea is to maximize the utility minus penalty. But a new variable y is introduced by Dinkelbach's algorithm. So the penalty is multiplied by y. So y can be thought of as the price of the penalty. And it turns out that if y is fixed, the new problem is convex in x because a is concave, b is convex, and therefore the new objective function is concave in x. So the problem is convex. And therefore, it can be easily solved by the standard numerical method. And after solving for x in the new problem, we can go back to update the new variable y to the previous value of the single ratio. And then you just iterate between these two steps. I first solve x in this new problem, which is convex, and then I go back to update y, and then furthermore I update x for the latest y. Okay, and amazingly, if you continue to update x and y in this fashion, ultimately you will converge to the global optimum of the original problem. And therefore, as we can see, both the two classical methods, Shannon-Cooper and Dinkelbach, can both deal with the non-convex single ratio problem by decoupling the ratio, even though they achieve that in two different ways. And the issue with the classical method is that they cannot be carried over to the multiple ratio case. I will talk about that in more detail in the next slide. Okay, so now let's move on to the multi-ratio problem. And now we introduce a sequence of A and a sequence of B. Again, we assume that each A is non-negative and each B is strictly positive. And each AI and BI constitute a ratio. And now we aim to maximize the sum of a bunch of ratios, AI over BI. And yeah, of course, the problem is still not convex at the beginning, so it's difficult to solve it directly. And a naive idea is to decouple each ratio simply by the Dinkelbach's algorithm. So you may decouple AI over BI, and then you introduce a new variable yi. But it turns out that the resulting new problem may not be equivalent to the original problem. So this approach won't work out. Actually, it's not easy to extend Shannon-Cooper algorithm either. So none of the classical approaches can be extended to multiple ratios. So this is the issue with the classical FP theory. And since the classical method cannot be applied here, the existing works mostly rely on the branch and bound algorithm to find the global optimum. And we know that the branch and bound is almost the same as the exhaustive search. It can incur an exponential complexity, so it's not suited for the practical use. Okay, in order to address all the above issues, we propose a new method called quadratic transform. Okay, before proceeding to the new algorithm, let me first review why the classical methods cannot work for multiple ratios. So let me set a bunch of goals we want to pursue for the new transformation for multiple ratio problem. The first target is to decouple the ratio. This is inspired by the classical method. So by decoupling the ratio, we can somehow make the problem easier to solve. And this is also true for multiple ratio problem. So basically, we want to decouple A and B, and the new objective function is denoted by G. Again, we use Y to denote the new variable introduced by the transformation. And the second goal makes all sense. So we wish to have the same solution X in the new problem as in the old problem. So this is the whole point of the transformation. We want the solution be the same, right? But the third goal is brand new. Aside from the same solution, we now further want the same objective value. So recall that y is the auxiliary variable, and we will optimize y for fixed x. So after we obtain the optimal y, we will plug y star into the new objective function g. And we require that the resulting g with the optimal y must be equal to the original objective value, which is the sum of ratios. So this is brand new. So this has never been studied this have never been considered in the previous literature. And the last requirement is also natural. When x is fixed, we want the new objective function g to be concave in, when x has been fixed, we want the new objective function g to be concave in the new variable y. And this is a natural goal because we want y to be easily updated when x has been optimized, okay? Otherwise, updating y can be another challenging problem. We want to avoid that difficulty, okay? And it turns out that if you look at Dinkelbach's algorithm, you can show that it satisfies all these goals except C3. And this is actually the fundamental reason for Dinkelbach's algorithm not working for multiple ratios. So now we pursue a new transformation that satisfies all these goals. And we can show that if we wish to satisfy all the previous 4 conditions, the only possibility is the quadratic transform. As you can see, we still decouple AI and BI for each ratio, but unlike Dinkelbach's algorithm, we now put AI inside the square root. You see, the square root is a concave function. Originally, A is a linear function, so somehow you curve up this function. So you somehow slow down the convergence of this iteration of this iterative optimization. So this is the bad thing, but the good thing is that now this transformation accounts for multiple ratios. It's not limited to a single ratio. So this is the advantage of this new method as compared to the traditional Dinkelbach's algorithm. After getting this new problem, we propose optimizing x and y in an alternating fashion. So first of all, we fix y and optimize x. Again, we assume that each AI is concave, each BI is convex. And you can see this composition function is still concave. So a concave minus a convex. So the overall is still concave. So this can be easily solved for x when y has been fixed. And after optimizing x, we look at y, and it turns out that y can be optimally solved in closed form. It's just the update to the square root of AI over BI. And we can perform that efficiently for each yi. Then we just iterate between these 2 steps, and we will ultimately arrive at a stationary point of the original problem, which is the local optimal. This is the best one can expect for a non-convex optimization problem. Okay. And more importantly, the quadratic transform can be readily extended to the matrix ratio case. So far, I discussed the ratio between 2 scalars, but the ratio can be also considered for 2 matrices. Yeah, for example, we consider the ratio between AI and BI. Okay, so the sum of ratios become sum of traces of matrix ratios. And it turns out that the quadratic transform continues to work. We still decouple AI and BI, and now we have this new problem. And then you can still carry out the iterative optimization between x and y efficiently. When y is fixed, the problem is convex in x. And when x has been fixed, each yi can be updated in closed form. Okay? So, this matrix version of a quadratic transform is of particular interest because many tasks in machine learning and signal processing take a matrix ratio form. Okay, so this is quite crucial. I will discuss that in more detail in the future slides. Okay, and I also would like to connect the quadratic transform to the famous majorization-minimization theory, namely MM theory. So MM theory is an important tool for non-convex optimization. So let me first quickly review what MM theory does. Suppose we wish to maximize a function fx. Because fx is not concave, and therefore it's difficult to optimize fx directly. So what MM theory does is to construct a lower bound to fx. And this lower bound is tight in the sense that g equals f at some point, but it's strictly below fx elsewhere. Then instead of maximizing fx, we consider maximizing g. And that will lead us to this point. And at this new position, xt, we will construct a second so-called lower bound, which is called surrogate function. And we will continue that. So after repeatedly constructing the lower bounds, we can ultimately arrive at a local optimum of fx. And we can show that the quadratic transform is doing exactly the same thing for the FP problem. So for the original sum of ratios objective, so what quadratic transform does is to construct a sequence of surrogate functions, namely the lower bounds, the tight lower bounds. Okay, so now we arrive at the first application case of the quadratic transform. Okay, so suppose we have a bunch of data points, and for any pair of data points, let's say I and j, we measure their similarity by using the weight wij. And the wij is given, and it takes on value between 0 and 1. So in particular, when wij equals 1, it means that I and j are identical. They're exactly the same. If wij equals 0, it means that I and j are completely uncorrelated. Okay, so they have nothing to do with each other. So in principle, we wish to partition the set of data points into k clusters. So intuitively speaking, we wish to put all those points that are similar to each other in the same cluster. In other words, we want to minimize the sum of similarities between two distinct clusters. And this sum of similarities between two clusters is referred to as the cut. Okay? But it will cause problem if we just minimize the cut, because then we will end up with putting all the data points in the same cluster. This is not good. To address that issue, it's common in the literature to consider the normalized cut instead. So we will normalize cut by the cluster size. So a cluster will be punished for taking too many data points in it. Okay, so a standard problem formulation for data clustering is to minimize the sum of normalized cut across the k clusters. Okay, so let me specify the problem formulation. So after some easy algebra, we can reformulate the minimization of the normalized cut as the maximization of the sum of ratios. Here, xik is the indicator variable. So xik equals 1 if data point I is assigned to cluster k, and it equals 0 otherwise. So why we have the first constraint? Because each data point I can only go to one cluster, okay? And for sure, xik must be binary. It's restricted to the binary set of 0 and 1. And you can see that this problem is difficult to solve for two reasons. First of all, this is a nonlinear discrete optimization. And the second reason is that even if we relax each x to be a continuous variable between 0 and 1, the problem is still difficult to solve because of its non-convexity. Okay? All right. So we suggest solving it by the quadratic transform. So basically, we will treat each ratio, we'll deal with each ratio by fp. And then we'll decouple the ratio. And then you can somehow convert this problem to this new form. And you can see that when y is fixed, this new problem is weighted bipartite matching problem of x. And we know that bipartite matching problem can be easily solved by many standard methods, such as Hungarian algorithm and auction algorithm. Okay, so it can be solved in polynomial time. And after solving for x, you go back to update y, and then you just carry out the iteration between x and y as before. Okay. All right. So let me show you some specific examples of the use of FP-based data clustering. So in this table, we can see 4 pictures, okay? And on the first column, we see the original the pictures, okay? So here, the picture consists of a large number of pixels. So each pixel can be basically thought of as a data point. And our target is to group all the pixels into just 5 clusters. And after clustering, all the pixels in the same cluster will be given the same color. So the target of this data clustering is to compress the image, okay? And as you can see, the 3 columns in the middle show the benchmark methods. They all come from the previous literature. You can see that we just compress the original figures into new ones, okay? And the last column shows the new images generated by FP-based method. As you can see, the pictures, due to our method, has a higher resolution. And you can see that the objects in the figures show more details. For example, the cow, the bus, and the car. It shows that our algorithm outperforms the existing ones. Okay. All right. So the previous example is about AI, and our next example is about application case is about signal processing. To be more specific, we consider multi-antenna signal processing. So let's consider a wireless network. So we have 3 cells. And in the middle of each cell, we have a base station, which is the transmitter. And we have a bunch of user terminals within each cell. And the aim of each base station is to transmit signals, independent data signals, to its associate user terminals. And here's the system model. Y is the received signal, H is the channel, V is the beamforming vector, X is the transmit signal, Z is the additive noise. And all these variables are given except V. So our target is to choose V properly so as to maximize the data capacity or the capacity of the data transmission. And turns out that this problem is super difficult. And in my community, the state of the art is so-called weighted minimum mean squared error algorithm, which is also called WMMSE algorithm. And this algorithm was proposed by the following 2 papers. I guess each of them has been cited for over 1,000 times. Okay, so this is a very famous algorithm in my area. So let me look at this problem more closely. Yeah, suppose we have multiple downlink cells, and each cell has multiple user terminals, and each base station has multiple antennas, and each user terminal has multiple antennas as well. And therefore, the beamforming vector V is a matrix, and this is the variable we aim to optimize. And given V, we can calculate the data rate of each user IK by using this formula. So this is based on Shannon's information theory, the channel capacity, okay? So basically, the data rate is a function of all the beamforming vectors, VIK. And our target is to coordinate all the VIK so as to maximize the total data rate throughout the network. Okay. So let me show more details about this optimization problem. So at the beginning, we aim to maximize a summation of the log determinants. And you can see that we have a ratio, actually a matrix ratio inside each log determinant. So we have seen that the quadratic transform can be used to maximize the sum of ratios. However, we do not have the sum of ratios here because each ratio is inside a log determinant. So we cannot apply the quadratic transform directly. Luckily, we have so-called Lagrangian dual transform. So its job is to somehow move the ratio to the outside of the log determinant. So after that, we can convert the original problem in this new form. And a new variable gamma is introduced by the Lagrangian dual transform. So gamma can be easily solved in closed form. And we focus on optimizing the primal variable v when gamma has been fixed. But v only appears in the last term of the new objective function. The last term takes a sum of ratios form. And therefore, we can readily apply the quadratic transform to the last term of the new objective function. And therefore, after Lagrangian dual transform, we further apply the quadratic transform to decouple each ratio in the last term. And then we end up with this further reformulation. So now we, aside from the original variable v, we have introduced two new variables. One is gamma, which is due to Lagrangian dual transform. The other is the y, which was introduced by quadratic transform. So if we optimize v along with gamma and y in an iterative fashion, it turns out that we just recover the well-known WMMSE algorithm exactly. So there's an intimate connection between WMMSE and the FP algorithm. All right. So let me further talk about how to improve the quadratic transform. So we have seen that WMMSE is just a special case of FP because we can use FP to derive WMMSE algorithm. And the WMMSE algorithm has been extensively used in the signal processing area. But we are still not satisfied with WMMSE for multiple reasons. The first reason is that WMMSE requires inverting larger matrices for each iteration. So some recent works propose reducing the size of the matrix by using some certain techniques. However, their methods do not always work. They require some certain strong conditions. And we are also not satisfied with the theoretical aspect of WMMSE. For example, the previous two famous papers only show that the WMMSE algorithm will converge to some station point, but they never show how fast WMMSE converges. And also, we have no idea what's the advantage of WMMSE algorithm as compared to any other universal optimization method, for example, the gradient method. And we also ask, can we further accelerate WMMSE? And I aim to address all these issues by proposing an improved FP transformation. Okay, so this is the rest of my talk. So let's first review what WMMSE or the quadratic transform does for the sum ratios problem. For ease of notation, let me just restrict our attention to a single ratio, but my argument can be easily extended to multiple ratios. Suppose we wish to maximize the trace of this matrix ratio. It's difficult. So what we do is to decouple this ratio by the quadratic transform. Then we introduce y, then we have this new transform. We have this new form of the problem. And then after some algebra, we can have this rewriting. So this is a quadratic function of the beam-forming variable v. And as you can see, we can show that C is a positive definite, and therefore you can get the optimal v by completing the square for each v. Okay, so from the traditional optimization perspective, this problem is easy to solve. However, in order to complete the square for each v, you have to calculate the inverse of matrix C. And this can be fairly costly because C may be a large matrix. Because the size of C is proportional to the number of antennas. And in the wireless networks nowadays, we have massive antennas deployed at the base station and also the user terminal. So we think this is impractical. We wish to eliminate matrix inversion from this optimization algorithm. To that end, we propose a new method called non-homogeneous quadratic transform. As you can see, this new transformation technique still converts the the matrix ratio objective to a quadratic problem form. However, you can see that we no longer have a matrix between V Hermitian and V. And then without this C, we can easily calculate the optimal V by completing the square. We no longer need to calculate the matrix inverse. So let me give you some geometric interpretation. So what quadratic transform does is to project some some point onto the surface of an ellipsoid, okay? And we know that this projection can be fairly difficult in the high-dimensional case. So what the non-homogeneous quadratic transform does is to somehow deform the ellipsoid into the sphere. And then the projection of the point onto the surface of the sphere is much easier, even in the high dimension. So this is where the advantage of the new algorithm comes from. And I also analyzed the convergence rate of the different algorithms. As we can see here, we have inequality. On the left-hand side of the inequality is the gap between my current objective value and the convergence value. So K is the iteration index. So f of x1 refers to my objective value after one iteration. F of xk is the objective value after k iterations. And on the other side of the inequality is the error bound, which depends on parameter lambda. As you can see, the larger lambda, the larger error bound, and therefore the slower convergence. And it turns out that the new method, non-homogeneous quadratic transform, has a larger lambda as compared to the existing quadratic transform. And therefore, the new method has a slower convergence in iterations. And therefore, the new method can get rid of the matrix inverse, but sacrifice the speed of the convergence. And here's the geometric interpretation of the previous result. As I mentioned, the quadratic transform amounts to constructing the lower bound for the original objective value. And we can show that the new method is constructing the lower bound as well. Fq is the lower bound due to the quadratic transform, and the Ft is the lower bound due to the non-homogeneous quadratic transform. As you can see, the lower bound by the quadratic transform is tighter, and therefore its lambda is smaller, and therefore its convergence is faster compared to the new method. Okay? So the new method is good in the sense that it can get rid of the matrix inverse, but it has a slower convergence. Can we fix this issue? Well, the answer is positive. This is based on the following key observation. It turns out that the non-homogeneous quadratic transform, you see, it's to update x and y iteratively. It turns out that it amounts to the gradient projection. Okay? Even though the choice of the step size is very weird, we will never see that in the conventional choice for the step size in gradient descent algorithm. Okay, and this connection is very important because since the non-homogeneous quadratic transform amounts to a gradient projection, we can leverage Nesterov extrapolation to accelerate its convergence. And this is a well-studied theory in the optimization society. So let me quickly review what's Nesterov extrapolation. Suppose right now we are at this position. According to the conventional gradient descent, we will follow the current gradient direction and move to this position. However, according to the Nesterov extrapolation, we assume that we have a heavy ball here, and it has inertia, and therefore it moves along the current gradient direction, and also it moves along the previous gradient direction. And by the combination of these two gradient directions, I will ultimately arrive at this new position. Okay? So the main idea is to incorporate this extrapolation scheme into the non-homogeneous quadratic transform thanks to the connection between non-homogeneous quadratic transform and the gradient descent. And the resulting new method is referred to as extrapolated quadratic transform. And I also analyzed the convergence rate for the extrapolated quadratic transform. Yeah. Yes. Yes, lambda actually is related to some Hessian matrix, the eigenvalue of the Hessian matrix. So it describes the second order behavior of the approximation. Okay. Yeah. For example, if it's equal to 0, lambda equals to 0 in this case. Okay. Yeah. For example, the Newton's method, it's a second order method, so its lambda is also equal to 0. Okay. Yeah. Okay. And we can show that yeah. So the convergence rate of this new method is characterized by this inequality. Oh, sorry. Okay, thanks. Okay, yeah, let me get back to my talk. So this is the error bound for the extrapolated quadratic transform. And we can consider, we can compare this error bound and the previous error bounds in the asymptotic regime where k, which is the number of iterations, tends to infinity when it's very huge. And we can show that the quadratic transform and also the so-called the non-homogeneous quadratic transform both have the error bound of big O of 1 over k. In contrast, the new method, extrapolated quadratic transform, has the error bound of big O of 1 over k squared. And therefore, when k tends to infinity, the extrapolated quadratic transform converges to the decision point more rapidly. Okay, so it has a faster convergence compared to the previous method. Okay, so let me show you some numerical results. So here we consider a 7-cell wireless network. We assume that each base station has 128 antennas, and each user terminal has 4 antennas for the signal reception. And the horizontal axis is the running time of each algorithm, and the vertical axis is the sum of rates, which is evaluated by the Shannon's capacity formula. And we have 3 algorithms here. The blue curve is the traditional method, WMMSE, which is equivalent to quadratic transform. And the yellow one is the first new method, which can eliminate the matrix inverse, which is called non-homogeneous quadratic transform. And the red one is the last algorithm I just introduced. It's extrapolated quadratic transform. As you can see that extrapolated quadratic transform converges really, really fast. After just 4 seconds, it almost converges. Okay. In comparison, the WMMSE algorithm is still far away from the convergence after over 20 seconds. Okay, so it's much more efficient compared to the traditional methods. Okay, so it's time to recap what I introduced in today's talk. I start by introducing classical FP methods. So they are good because they can solve the non-convex problem by decoupling the ratio. But their use is fairly limited because they can only account for the single ratio problem. They do not work for multiple ratios. And next, I introduced one recent method called quadratic transform, and that works for multiple ratios. And I also show that quadratic transform encompasses the well-known WMMSE algorithm as a special case. Next, I point out that the main issue with the quadratic transform is that it requires inverting big matrices for each iteration. And we propose a new method called non-homogeneous quadratic transform that can sidestep the matrix inversion by transforming the sum ratios in a different way. Okay? But this new method is faced with a new issue, is that it slows down in terms of the iterations. And to remedy that, we take advantage of the link between the new transformation and the gradient projection. And then we can leverage Nesterov extrapolation to accelerate its convergence. And we prove that it has a faster convergence compared to both WMC and the non-homogeneous quadratic transform. And lastly, I would like to point out that the applications of the FP are by no means limited to signal processing and wireless communications and just data clustering. They have a wide range of applications because many key measures are fractionally structured. For example, the signal to interference plus noise ratio. This is extensively used in the communication system, and also the Cramer-Rao bound, which is extensively used in statistics and also the radar signals processing, and also the facial information and energy efficiency. There are lots of applications over there. Okay. Okay. Thank you. That's all for my today's talk.
So, is there any questions?
Wait, can you also apply acceleration to the version that uses matrix inversion?
Yeah, for sure. Yeah.
Did you experimentally compare like if you do that?
Yeah. So for simplicity, I only show the scalar ratio case. Yeah, we have an extension for the matrix ratio.
And how does it perform? Just out of curiosity.
I don't remember it. Sorry, it's not in my latest paper.
And also, I had a very naive question on the plot. Why is there a like an elbow for WMS? Like what's going on?
Oh, why we have a?
Yeah.
Okay, yeah, because it means that WM's algorithm just finished one iteration after, yeah, so it's very slow. Yeah, so it's not smooth out. Yeah.
Thanks, Professor. I'm a senior high, so Chinese, please.
For sure.
您前面提到一个 data casting， 就是那个数据的压缩。
Here, right.
我是不是可以把它理解为就是您能做到数据压缩的原因是把它这两个东西的特征部分提取出来了，然后作为那个压缩的标准。
Okay. So there's something called entropy， 就是熵是描述你的那个混乱的程度。
哦，用 S。
就 if the entropy is high, you have to use lots of bits to describe this stuff. So at the beginning, each pixel can be fairly different from each other. So you have a high entropy, and after data clustering, you make all the pixels in the same cluster the same color. So you reduce the entropy. So that's why you can compress the image, right?
就像后面您提到的那几张 bus 和 car 那个图。
对，就本来有些色块都是不一样的，但是我把它有些色块都用一样的颜色来表示，就降低了它的 entropy。然后信息论里面就是你 entropy 越低，你的压缩的 bits 可以用的越少，也就是你可以达到一个压缩效果。
它就是从这个效果就可以看出原来的那个图，因为您提到传统的那个Fractional programming， 它有那个 max 像 ABB 的这种形式，然后后来您把它推广到矩阵的方面和那个二次变换，就是如果是一个后边您还说了一个那个误差，就是那个 A， 那个大 A， 就是如果我能去测出这么一个误差，是不是可以用它去提取像是机器的功率的特征，然后可以用来预测以后的 指标。
这误差是什么意思？
就是您后边不是提到一个 a 吗？
你说 error bound 吗？是在哪一块？
是在后面一个。
是往前还是往后？快结束了。
就是一个，好像是一个，我看那意思好像是作为衡量差距的一个指标，就是。
是在哪一块？大概是在讲 application 的时候，还是在讲
I don't remember。